Right, so we'll treat spherical mirrors first as an example of an optical system that can form a real image by refocusing rays that are diverging from a source. So a spherical mirror is a section of a spherical polished metal shell, for example. So you take a spherical shell that's metal, you polish it so it reflects well, and you cut a chunk out of it. So when I draw it like this on the page, don't think of it as a bent sheet of paper. Think about it as a bowl. Okay, so it's as if you took a spherical, again, a sphere, and cut a bowl out of it. And you could look at, reflection off of either surface, off of the back surface. This would be what we call a convex mirror on this side. Or you can look at reflection off of this surface. This would be concave side. Okay, and they do very different things to light. Okay, so oops, didn't mean to do that. If I look on the concave side and put a point source here, what it's going to tend to do is to refocus the light. Okay, so I'm going to get basically light rays that bounce like this and get reconverged to a point, or nearly a point, as I'll say. Okay, and so I'll refocus the light rays to a point and form what I'll say is a real image. Okay, let me clean that up. If I go to the other side, the reflections will tend to be diverging. Okay, so if I do equal angle, I tend to get reflections that look like this. Okay, and this will tend to form the virtual images that we have already talked about. Okay. So as we'll see, the concave side can form real images and virtual images, and the convex side will only form virtual images. Okay. All right, now we choose spherical mirrors because they're easy to analyze mathematically. It turns out that spherical mirrors aren't actually perfect focusers of light, except if you're right at the center of the sphere. If you're standing at the center of the sphere and you have light, from a source, it's going to go out, hit the sphere, and come right back to the same location. And in that particular case, the light rays will focus back to the center of the sphere. But if I go off that location, I will find that rays will tend to focus near one particular spot, but not perfectly. So it turns out if you want to build a mirror optic system, take for example in a telescope like the Hubble telescope, you don't want a spherical mirror. You want an aspherical mirror, something that has some departure from being spherical to allow the focus to be better. Okay. So what we're going to see is that spherical mirrors will focus to a point only if you consider light rays that come off of that come at the mirror at a shallow angle. Okay, so let's set that up. So let's imagine we have a mirror here, and let's say this is the center of curvature of the mirror here. And so some radius of curvature of the mirror is r. And what this means is if I were to draw radial chords here, from this point, they always intersect the spherical surface as a normal to the surface. Okay, as drawn there. Okay, if I take an object now, and so let's just, for the moment, take a point here. Again, if I consider rays that come off of this object, let's take a ray that goes through the normal that I've already drawn here. So take a light ray that goes right there. You're going to find an equal angle reflection, and it's going to come down like that. Okay, and I can pick other rays. I'll try to pick something that's symmetric on the other side. Pick one here, and again I'm going to have equal angle reflection, and it's going to go through some point on the axis here. Okay, and I can take a number of different rays and look at that. Now, if we assume, okay, let me make some definitions here, and then I'll talk about the assumptions. So we're going to again define the location of the source relative to the mirror. We're going to use the vertex of the mirror, which is here. This distance is going to be called S. That's the distance to the object that's emitting the light and forming the image. And this location is where the image forms. That's where the rays converge to. And that will be distance S prime. Okay. Now again, if I look at this point, I see rays diverging away from it. So if there's an observer over here watching, these rays appear to be coming from that point. which is and they actually are in this particular case. They are actually coming from that point, but not because there's a real object there, of course. These are rays that have been refocused and then rediverge again as if there were an object there. Okay, so we call this a real image. Okay, so let's see. Let me clean this up again. Okay, let me do this. So let me go to your textbook because I don't want to write out everything again, but let me just point this out to you. I don't want to take you through the derivation. So if you look here in your text, there's a nice drawing of this situation. I have an object P. I have an image at P prime. This distance is S prime. This distance is S. And basically what they've done is mark this drawing up with a bunch of angles. Okay, and this distance H and this distance delta. Now you can basically look at this and make some geometrical arguments. And let me go to the next page here and I'll show them to you. Come on, there we go. Okay. So you can write these expressions down based on the geometry of the previous problem. So this set of expressions will give you where the image location is for an arbitrary angle alpha. Okay. But it turns out that the image location, S and S prime, will vary because of that alpha. Okay, so depends on the angle that the ray comes in. So if I look back here, for a particular alpha, this point P prime might move around. Okay, and this is why a spherical mirror isn't a great optical system by itself. If I have a big mirror that takes all these rays that have different angles alpha, I'll end up getting not a focus to a point, but a focus kind of to a line, and so it ends up with a very fuzzy image. And instead, what you often do is have a small mirror, so a mirror that is not very, very big, so that alpha can stay small. Now, if you do that, going back to this page again, okay, if you say that alpha is small and the other angles beta and phi will be small in that limit too, you can approximate tangent of alpha as alpha, and that's what's done here. And you end up with the following approximate relationships. And if you go back to this expression up here, which is another geometric argument, you come up with this expression here. Okay, so this becomes, for small angle alpha, it turns out the location of the image is independent of alpha, which is good because you want all rays that at any alpha that strike the mirror to come to us the same point. That's true in the limit where alpha is small. You get a well-defined focus point. This is what's called the paraxial approximation here. Okay, so this expression can be used to find the location of an image in these spherical mirror systems for small alpha. Okay, let me get that out of the way, and so I'll write it here. All right, so the expression is that 1 over S plus 1 over S prime is equal to 2 over R. Okay, for the mirror. All right. Okay, so this length here, inverse length, R over 2, is often written as the focal length as the mirror. So we'll often write it like this: 1 over S plus 1 over S prime is 1 over what's called the focal length. So in the case of a spherical mirror, the focal length is R over 2. Now, what do I mean by the focal length? The focal length is the location of an image of an object that's at infinity. Okay, and that you can see here. If I put in S infinity, then you see this goes to 0, and you get that the object is located at the focal length. Okay, or a focal length away from the mirror. Okay, now when an object's at infinity, let me I won't draw it out at infinity, but it turns out the rays have to come from very, very far away. So the rays can't have any angle to them relative to the mirror. If they do, they'll miss the mirror. If it's a finite size mirror, then any ray at infinity that's not going straight to the mirror is going to miss the mirror high. Okay, so if you have an object at infinity, the rays come in perfectly straight, and it turns out if you reconstruct this, let me see if I can get my Um, let's call this the center of the mirror, R. So R over 2 is here. This is the focal length, R over 2. Let me try that again. R over 2. Okay, and I'll switch colors. So rays that come in parallel to the axis of the mirror, which is here, will be focused through this location, which is the focal length R over 2. Okay? All right, you can draw as many rays as you like. That's what's going to happen. And in fact, these rays, by definition, satisfy the paraxial approximation because alpha here is 0. Okay, and so all these rays, no matter how high up on the mirror you go, will satisfy this condition. Okay, all right, so one more thing before I quit, and that is the consider not a point object but an extended object. So if I have my mirror, let me just draw my axis here. I have a spherical mirror. Let's put an object that's not a point, that has some finite extent. We can draw a person. How about that? Okay. So there's some height to this person. That's y. And some distance s. And let's say here's our center of the mirror. Now I can construct this image, and I'll go over this more in class using a graphical technique. And so let me go through and do that. So let's take rays that are on, the head of this person. So what I can do is let's take a ray that goes perfectly flat, horizontal, towards the mirror. Now that's the same kind of ray that would come from an object all the way out at infinity. Now this is just one ray from this object that's much closer to infinity. I have to draw other rays. For object at infinity, all the rays are straight across. Okay, but this is just one. But I know where this ray goes because of a ray that goes straight. Okay, and so this ray that goes flat towards the mirror, straight towards the mirror, will go through R over 2. Okay, so there's my focal length here, F. So I can draw that one ray here. Another so-called principal ray that I can draw to help me construct this image is the ray that goes to the vertex of the mirror. So I know that if I take a ray to the vertex of the mirror, it's going to come back through a point that's equal distance from the top of my head on the other side. So I can draw it like this. I didn't quite make that, but that's close enough. And so now I can see I've found a point where the image is going to be, which is right there. Now I can draw another ray, which I'll skip doing. But you can see the head of the person is going to show up down here. Now I can go through and do the body and the legs, and I'm going to find the person will show up inverted. Okay, just like this. Okay. And so let me do a couple things here. So if I take take this principal ray that goes through the vertex of the mirror, okay, I have two similar triangles here. Let me try to draw that. So I have a triangle here, okay, and I have side S and Y, and then there's another triangle. Let's pick a different color. That's here. Okay, this side is S prime, and this side is the height of the image, which is Y prime. And so if I look at this, what I find is that there's a relationship between S prime, and Y prime. Now, if you remember, we defined the magnification to be Y prime over Y. So from these similar triangles, what I can prove is that the relationship between Y prime and Y is the same as the ratio of S prime over S, but with a negative sign. Okay? And so if I know the location, if I can map the location of the image, I can find the magnification. Now the minus sign means that the image is inverted. So this is why you get an upside down image. Okay? All right. Let me stop here. I'll spend more time in class going through examples of how images are formed. We'll see that there are situations where the image is not inverted and the image is not real when we look at this mirror. Yeah, anyway, I'll stop there.